The last lecture we were talking about the free boson. So the action was 1 over 4 pi alpha prime x dot squared minus x prime square d tau d sigma. You remember that we expanded, we wrote down a mode expansion, wrote down the most general solution for this action. So we wrote down, now just to switch to, okay, so now to match Polchinski's conventions, we're going to do this mode expansion again this time, but carefully keeping track of normalizations so that they will match what Polchinski wants. Okay, so let me write down the expansion that Polchinski has. He presents it in Euclidean space on the plane, and then we will go back. Yeah, we will go back and try to track it down. So, first thing is this: when we have the cylinder that we were working in here, time here is, let's say, Lorentzian, and then there is a sigma coordinate. Okay. Now, as you remember, the way we're going to do the procedure we're going to employ to go from the Lorentzian cylinder to the plane is first go from the Lorentzian cylinder to the Euclidean cylinder, and then the Euclidean cylinder to the plane by conformal transformation. Okay. So, what's the relationship between Lorentzian time and Euclidean time? Well, this is there's always a standard relationship, right? The way I remember this is as follows. In quantum mechanics, we have a path integral involves an e to the power I s. S has an x dot squared minus v potential, mx dot squared minus v. I'm just going to look at the potential term. So we have v dt Lorentzian, okay, with the minus because the action came with a x dot squared minus v. Okay. Now, we want to do the continuation that will make this e to the power minus v t Euclidean, right? Because we want the Euclidean continuation is the one that makes the action damped down. We want minus v times t Euclidean. And so you see that this will work if we define t Euclidean is equal to I times t Lorentzian. Okay. So say we started with the Lorentzian time here. We will move to Euclidean time via this relationship. Okay. So now, so let us, the guy that is Euclidean time here, on this cylinder, once we've gone to Euclidean space, we have this coordinate sigma, and then we call the Euclidean time coordinate. This is sigma 1, and Polchinski calls this guy sigma 2. That's Euclidean time. And he works with a complex variable w, which is sigma 1 plus I times sigma 2. Let me check that. Yes, he works with sigma 1 plus I times sigma 2. So what was sigma 2 in terms of Lorentzian time? Sigma 2 was equal to I times t Lorentzian, or t Lorentzian was equal to minus I times sigma 2. This we have to keep in mind. Okay? Then the next thing he does, in going to the plane, okay, is to define z is equal to e to the power minus I omega. Okay. Now let's check that this e to the power minus I omega has the properties we want. We wanted that at that very early Euclidean times correspond to the origin. So very early is large negative sigma 2. Large, yes, so I times minus I is 1, and then if sigma 2 is large and negative, we go to the modulus goes to 0. Okay, so this conformal map has that property that it takes very early Euclidean times to the origin, very late Euclidean times to infinity. Okay, So this is the conformal map. This is the conformal map that takes us to the plane. This is the Z plane. Okay, and with this conformal map, the expansion that Polchinski writes down is that del x is equal to del x is equal to minus I times square root alpha prime by 2 sum over alpha m z to the power m plus 1. M is over all minus infinity to infinity. M equals 0 is made up of some combinations of x0 and p0. Right, but M is overall minus infinity. Okay, and he tells us that the commutation relations are alpha m, alpha minus n is equal to alpha m, alpha minus n is equal to m delta mn. Okay, we want to check that our canonical quantization, we want to check that our canonical quantization gives us exactly the same thing, and thereby also identify these alphas with what they were in Lorentzian space, and that is our goal. Okay, so let's keep this all this stuff here on the board and move to the next board. So our action was S is equal to 1 by 4 pi x dot squared minus x prime squared d sigma d tau. Okay, now if I take this first thing I'm going to do is to take this expansion and unintegrate it. Okay, what does it say about x? Yes. Commutation relation won't have I, because you see, these are going to be the modes of a harmonic oscillator. Actually, in what we did last time also, we didn't have an I. The Poisson brackets had an I, and therefore the commutation relations didn't have an I. We're just going to repeat what we did last time, but a little more carefully with the normalizations. Okay. Okay. So this expansion here is x is equal to, and now we just integrate each of these terms. Okay. So the minus goes away, and integral of is minus m. So we get I alpha prime by 2 sum over m alpha m by z to the power m plus z to the power m. Okay, so this is the expansion that Polchinski. There's also the zero mode which involves logs. I'm not writing that. We'll come back to that as well. Okay, so we're ignoring the zero modes here. This is accurate. Okay, so let's take this z to the power m. What? M is in the denominator. Thank you. M is in the denominator, 1 by m. Thank you. Okay?
For negative m, this x field will have some singularity at the origin?
For negative m, the x field will have a singularity at the origin. That is correct. And this is because this x field, when acting on the vacuum, produces a state. Okay? So the states that have singularities at the origin are those states which, in their action of the vacuum, don't annihilate.
Can you repeat it again?
The states that have the terms that have singularities at the origin are the coefficients of those terms whose action on the vacuum gives you something non-trivial. Yes, we will study all of this in great detail in this lecture. Okay. Okay. So this is the expansion we're instructed to make. Now let's translate this back to the cylinder. Okay. So if we translate this back to the cylinder, we get yes, good. If we translate this back to the cylinder, we get I square root alpha prime by 2. This doesn't change. Well, what was this z? Z was e to the power minus iw, so the sum over m, 1 by m alpha m e to the power minus iw. Iw was sigma 1 minus plus I sigma 2. There's an m here, because this was z to the power m. Okay? And sigma 2 was T Lorentzian. Okay? So now help me get my signs right. I get plus I T Lorentzian. So minus sorry, say it again. Where should there be a?
It's 1 by z.
It's 1 by z to the power m.
So that will be plus I.
Plus, thank you. Yes, thank you. So plus I m, yes, thank you. Excellent. So now, right. So I times I is minus, and minus times I. So it's minus I m. So tell me if I got this right. So I square root alpha prime by 2 sum over m 1 by m alpha m e to the power I times I is minus, and then we get a plus I. So minus I m t, if t is T Lorentzian, plus I m sigma. Okay? Or equivalently, this is I sum over alpha prime by 2 sum over m 1 by m alpha m e to the power I m into sigma minus t. Yeah, sounds good. So the positive m modes come with e to the power minus IMT. That's what we normally call positive energy behavior. So it behaves like the the annihilation operators of a harmonic oscillator. Whereas the negative m modes come with e to the power IMT and behave like the creation operators of a harmonic oscillator. Yeah.
When we go from this plane to a cylinder,
Yes.
shouldn't we be worried about the dimension of x?
We should be worried about the dimension of x, it's true. But x, really what we should be worried about, right, as we will see, x itself is an ill-defined field. Del x has dimension 1. We will see this all this class. Okay? And it's this extra 1 here is a consequence of that. Let me explain that in more detail. In going from one place to another, we need a factor of del z by del w, let's say del w by del z. Right, because if you've got a dimension 1 field, because that's the transformation factor for a field of dimension 1. Okay, this del w by del z, since w was e to the power minus iz, z was e to the power minus iw. So z was e to the power minus. So let's do del z by del w. Since z was equal to e to the power minus iw, del z by del w is simply minus I times z. So for each extra dimension 1 field, okay, so if you've got a field of dimension m, you will have an extra factor of z to the power m times I to the power m. Okay? That's really why Polchinski put the del x there with the minus I and the z to the power m plus 1. Okay? But all of the dimension of del x comes from del. As you will see, x is not really a primary operator, but to the extent that it's an operator, it has dimension 0. Okay? So all of this transformation here was happening because of del. So when we're dealing with just with the x, we can forget about that factor. That factor will be automatic because it will come from the del. Okay? Yeah, so it's a good question. I'm knowing the answer and writing it down. But of course, I'm free to make any expansion I want. Okay, so this is the expansion I'm making. I just wanted to use this to get all the normalizations right. Okay. And in addition to this, of course, this was only for the left movers, or the right movers. We should also put in a similar expansion for the left movers. That will be contained in del z bar of x. You remember, x was a function of left movers plus a function of right movers. When we took the derivative with respect to z, that projected out the left movers. Okay? There's a similar expansion for the right movers, left movers. Okay? There's a similar expansion for the left movers. I'm not writing it down because it behaves exactly the same way. Okay? Now let's see. Let's repeat our canonical quantization and check whether we get the same commutation relations as Polchinski. Okay? We're going to check this just now using commutation relations. I'll check it again for you using contour methods in 2 minutes. Okay? So what were our commutation relations? Our commutation relations came from the symplectic form 1 by 2 pi alpha prime integral d x dot delta x dot wedge delta x. Remembering that this is dp wedge dx. Okay, the coefficient of this inverted is the Poisson bracket in terms of dx wedge dp. Okay. Then what did we do? We put in this expansion. Now we will put in the expansion like this. Okay? So we put in this expansion here. And we got an extra factor of m from here. We got an extra factor of m from here when we did it. So there were 2 m's. Okay? And then we get 1 extra factor of m. So the total number of m's is like a 1 over m. Okay? And we get 2 pi is removed because we do the integral over sigma. So we just have 1 over alpha prime. And then each term comes twice because we have the n and minus n term here, or vice versa. Do you understand the same mechanism that ensured that the left movers and right movers did not contribute? The same mechanism that ensured cancellation of the 2 terms between left movers and right movers here doubles things up. Okay? So this whole thing will be with a 2 by alpha prime. There will be an m, and then there's some factor of I. Okay? That factor of I I'm going to, we could of course find, but I'm going to provisionally write as I. Maybe we'll have to change it. We worked it out last time. Okay, so there's that factor of I. I just want to get the remaining normalizations correct. Okay, is this clear? Okay, but in our expansion here, we had this I alpha prime by 2. So we get this extra alpha prime by 2. Okay? So this cancels. So up to the plus minus, which I'm not rechecking, we have 1 over Im. Okay? This was, so the Poisson bracket then, okay, I think it was minus 1 over I. The Poisson bracket will involve this when we write this, so it will be minus 1 over Im d alpha m wedge d alpha minus m. Is this okay? Okay, up to the sign which I've not rechecked. We worked it out last time, right? Up to that sign which I've not rechecked, do you see that all other factors are like this? This is an I, not a 2. Okay? So therefore, this is the symplectic form. So the Poisson bracket will be alpha, maybe this is plus, let's see, alpha, okay, let's write it, yeah, I think minus with this, alpha minus m and alpha m. So the Poisson bracket will be alpha m, alpha minus m will be equal to I times m, 1 over that factor. Because the symplectic form and Poisson bracket are inverses of each other. Is this clear? Okay. And I'm so sorry about that sign. Okay, and then the rule is that once you've got Poisson brackets, you multiply by a factor of I to get commutation relations. Okay, so we will get alpha m, alpha minus m is equal to m, in agreement with what Polchinski had. Clearly we have this delta function because it only coupled things with equal and opposite momentum. Is this clear? Up to the sign, which I'm sorry I'm not checking again. You can look up your notes last time. By the way, in our notes last time we worked with e to the power plus imt. So you'll have to account for that to get that sign right. Polchinski has an e to the power minus imt, so interchange the m and minus m. Okay, but if you check it, you'll see that the sign was also correct. Okay, so you see that this expansion, this canonical quantization of our scalar field, when recast in Euclidean space, okay, and taken to the plane, becomes an expansion like this: x is equal to that kind of thing, or del x is equal to that kind of thing. Now, the main point I wanted to make from this discussion over the last 10 minutes, today's class, and the last 10-15 minutes of the previous class, we will have much better ways of checking the commutation relations. That was not the main point. The main point I wanted to make is that alpha m and alpha minus m on the cylinder were daggers of each other. Okay? In our expansion here, yeah, excellent. You see this I here. Okay, so let's take this expansion and complex conjugate it. Okay, suppose we take this expansion and put it back on the plane, right? Sorry, put it back on the cylinder. So this expansion here was this expansion. Now let's do a complex conjugate of this. Okay, think of all these just as plain numbers and complex conjugate. Okay, what are we going to get? This whole thing turns into, so let's look at I'll rewrite that expansion. So that was I square root alpha prime by 2 sum over m 1 over m alpha m e to the power I m into sigma minus t. So x, or really the right moving part of x right, let's call it, is this. So x complex conjugate is what? So this gives you a minus sign from here, okay? Square alpha prime by 2 sum over m 1 over m alpha m star e to the power minus I m sigma minus t. Is this clear? Okay? Now, this has become minus m. If this field was real, these two have to be equal to each other. Okay? So this should have been written with a factor of minus m, but that's this extra minus sign. And so the way that these two guys are going to, that this expansion is real, is if alpha m star is equal to alpha m. The minus sign, this I was needed for that conclusion. What? Alpha minus m. So in our expansion on the cylinder, these coordinates that we expanded, the coefficients in terms of which we expanded our solution, were obviously complex conjugates of each other, just as a classical statement. Okay? This turns into the statement in canonical quantization that these two operators are Hermitian conjugates of each other. Okay? On the other hand, when you look at these operators on the plane, they don't at all look like Hermitian conjugates of each other. Because if at all, if you did the naive complex conjugation on the plane, what you would conclude, you think, is alpha m is the complex conjugate of alpha tilde m, where alpha tilde m is the coefficient that appears in the z bar part of the expansion. Because you would tend to complex conjugate and take z to z bar. Okay? But remember, the notion of complex conjugation we will always use is what was inherited from the Lorentzian cylinder. Okay? So because when we continue back to the thing that is really physical, namely the particle moving on the Lorentzian cylinder, that really has a Hilbert space interpretation, all of that. Alpha m was the complex conjugate of alpha minus m. This is the dagger condition we will use all through. Our Hilbert space is really obtained on the Lorentzian cylinder, and then whatever we get is sort of just pulled along onto this z plane. Okay? So though we will do expansions like this, it will always be the case, certainly in this case it's the case, that that this expansion is accompanied by the commutation, the hermiticity condition, alpha m is equal to alpha minus m dagger. Alpha m and alpha minus m are complex, are daggers of each other. This of course goes very well with the commutation relation. These are like commutation relations for harmonic oscillators, and when we study harmonic oscillators, things that obey these commutation relations are daggers of each other. Okay? So it's what you would expect, but it seems confusing when seen from the point of view of this plane. The point again is that commutation relations, hermiticity conditions, are always thought of in Lorentzian space. We have to make when we make a choice of Lorentzian space, we make the one that agrees, whose Hilbert space will agree with the state operator map. So we want Lorentzian space on the cylinder. Okay, this is how we always think of the theory. Is this clear? This is very important. So though it doesn't look it, alpha m and alpha minus m are daggers of each other. And the way to see this is just go back to the Lorentzian cylinder. Clear? Okay, excellent. Okay, now that we've got this out of the way, we're going to do a couple of, one quick exercise. The quick exercise we're going to do is to check this commutation relation directly from this expansion. In order to do that, I'm first going to work out x of z prime, this expectation value on the z plane. This 2-point function, time ordered 2-point function on the z plane.
When you would like to see the action of this del x on the Hilbert space,
yes,
you would have to go back to the
Lorentzian space or do radial quantization. We're going to do a lot of that. Hang on to the end of this lecture. Okay? Radial quantization is mimicking what happens on the Lorentzian cylinder. So we'll always do radial quantization. Okay? We'll find Euclidean methods to do this, but always, whenever we're in doubt, you go back to Lorentzian space. Okay. So first let's evaluate for this theory x of z prime. This 2-point function. How do I do this? Well, of course, what I'm going to do is standard, but there's a sort of nice way to think of it, which goes as follows. We're working out the following path integral. Del x e to the power minus action. Our action was 1 over 4 pi, and then d alpha x. Yes? 4 pi alpha prime. Yes, please go. Okay. Del bar. So the full expansion was z was this plus, so this is z right mover. The full x is equal to x, the zero mode part, plus the right moving part plus the left moving part. And left moving part is expanded completely similarly. It's expanded as xl is equal to I by square root alpha prime by 2 sum over alpha tilde n by m z bar to the power m. M runs from 1 to infinity. Minus infinity to infinity, excluding 0.
So x is a sum of these?
X is a sum of these two. How did we know that? From Lorentzian space, if you remember from last lecture, we had that the full set of solutions was the sum of left movers and right movers.
So
Just the classical solutions. Classical solutions are left moving and right moving. Yeah. So that's why X was a sum of. Okay, if you start with Lorentzian space, do the canonical quantization, just go back here. You see that this happens. The left movers and right movers are functions of Z and Z bar respectively. That is clear. Yes, Nikhil? Can't hear you. These are the expansion of the fields, but we are writing down the expansion of the solutions. You see, we're putting in, had we done the expansion at one time, it would be the expansion of the field. But we're putting in the time dependence. So it's classical solutions. Right? If you want to think in an operator language, it's the operators evolving according to the Heisenberg equations. We've put that in. Right? But just think of this as classical phase space. It's least confusing. Okay, and then that we can canonically quantize that. Fine. Okay. Is this clear? Fine. So it's the sum of the two just because classical solutions were the sum of the two. Just for that simple reason. Okay. So let's go back to our path integral here. We have this path integral, which is a path integral over x of this stuff. Now, I want within the path integral to find a 2-point function of x. Okay? So I use this lovely trick. It's called the trick of Schwinger-Dyson equations. Instead of starting with this guy, I start with an insertion at some value of sigma. X inserted at some value of sigma. Okay? And then I do the following. I notice, so I'm rubbing this out. I notice that if I do del by del x of sigma prime dx, this is equal to 0. Why is this equal to 0? Because it's an integral of a total derivative. Integrals of total derivatives are always equal to 0, provided boundary terms vanish. Where in Euclidean space, the action falls off exponentially fast at very large values of the fields. So, so presumably all boundary terms vanish. So this is just 0. Is this clear? Okay, I take x sigma to be some very large, x sigma prime to be some very large number. The action will go to 0. Yes? It's like taking derivative of definite integral, but you know the definite integral has boundaries. And so we are going close to the boundaries, but the function vanishes at the boundaries. Boundaries are infinity. And the function, the integrand vanishes at infinity. Therefore, this is 0. Okay, it's just values at the boundary points, and that's 0. Okay? But now we can open that out.
Sigma and sigma prime are
different points. Okay?
By sigma you mean sigma 1 and sigma 2.
Exactly. I'm specifying sigma 1 and sigma 2, sigma 1 prime and sigma 2 prime. Is this clear? Now I can open this thing out. This derivative here is by definition a delta function. What about this guy? Well, this guy is, we bring this down, differentiate with respect to x. Okay? There are two places where we can differentiate this guy and this guy. We take them both, they're both equal. Before doing the differentiation, it's sort of convenient to integrate by parts. So I'm writing down what we get, and you tell me if you agree. We get 1 by 2 pi alpha prime, 2 pi from 4 pi because there were two terms. And then we get del squared of x at sigma prime. This into e to the power, I'm just calling it s, dx, this is equal to 0. Will contain what? I can't hear you, louder. X of, I'm differentiating with respect to sigma, will contain x of sigma. Thank you. So as Nikhil pointed out, this thing just is there. I'm using product rule. X of sigma times 10. Okay? Now, sigma and sigma prime are just coordinates here. Okay? So this del square out here. Okay, so what is this equation? This equation is del square of 1 by 2 pi alpha prime, del square of x of sigma prime plus delta 2 of sigma minus sigma prime is equal to 0. Is this clear? Okay? And therefore, this quantity is obeys the equation del square x of sigma prime is equal to 2 pi alpha prime delta of sigma minus sigma prime.
So there should be an expectation value.
With a minus, sorry. Yeah. There should be an expectation value of this. Yes, but this is just a number. It's not got any operators in it. So that's the same as the expectation value of 1. So while I did, in going from here to here, I used the fact that expectation values are defined by path integral of quantity divided by path integral of 1. So I've divided both sides by path integral of 1. Okay, because that's how we normally define expectation values. Okay, so here this became an expectation value. Here it was delta sigma minus sigma prime times path integral of 1 divided by path integral of 1. So it was just 1. Is this clear? Yes.
So the delta function,
Yes.
I would think that it should be a delta functional of x sigma and minus x sigma, right? Is that?
I didn't understand. Oh, no. You see, this here within the integral is just a number. Del x of sigma prime of delta of sigma is 0. Sigma is not equal to sigma prime. You see, x within path integrals. So they're just functions. We're just doing a functional derivative of functions.
Right.
Okay, so that's just delta function. Right? Okay, excellent. So that's one of the nice things about doing path integrals. Maybe we're actually dealing with some complicated, I don't know, Hilbert space, blah, blah, blah. But at every stage, you're only dealing with functions. Okay, is this clear? So, okay, now all we have to do is to solve this equation. We solve this equation subject to reasonable boundary conditions that the thing is, let's say, rotationally invariant. Okay? So of course it's very easy to solve this equation. It's the same kind of equation that occurs in electrodynamics. Right? We want del squared is equal to delta. So we write this is the same as saying that now we can turn this into a Gauss law kind of thing. So the integral of the electric flux. So del squared is del dot del of x. So del dot x integrated over the unit circle or any circle has to give us always this flux 2 pi, this flux, and therefore it must be that del x is equal to r hat times with a minus by r into alpha prime. So that we get the 2 pi is right. The 2 pi comes from the integration over the circle. The 1 by r and the r cancels. The length of the circle cancels. Okay? And therefore, but now we can ask, what quantity has this property? Well, clearly, minus alpha prime times log of r. When I differentiate, its gradient is r hat divided by r. Is this clear? Okay, so you understand what I'm doing, right? I've set my origin at one of the points, and I'm working as a function of the other. Okay, and so I can write this as minus alpha prime by 2 into log of z bar, because z bar was r squared. Okay? And so we conclude that x of sigma, let's say x of 0, is equal to minus alpha prime by 2 log of z bar. Or if we want x of sigma prime, it will be z minus z prime into z bar minus z bar prime. Okay, of course, all this you know, right? You know in some language that this is right. Yeah.
Z and Z bar variables are all dimensionless.
Z and Z bar, why do you say dimensionless?
Because we are taking log of them.
No. Okay, it's an excellent question. Excellent question. So they're not really dimensionless. And this is a problem. So this thing needs, as you say, a length scale somewhere in the middle. So let's say we put in some lambda square here, some mass scale there. Okay? So secretly there is that mass scale involved. Why didn't that mass scale come up in our derivation? It didn't because our derivation only involved derivatives. And log of that mass scale is a constant. Okay? So to our solution, you can add in any constant. So fine. Now, in normal dimensions, by which I mean dimensions 3 and greater, that constant can be determined by the boundary condition that the correlation function fall off at 0. Instead of log, you would have got a power. And you wouldn't allow constant plus power, you just take the power, because by cluster decomposition, 2-point functions have to go to 0 if the 1-point functions were 0. Okay? The problem here is, as you very correctly point out, Omkar, the problem here is that these correlation functions don't die off at infinity in this dimension. They blow up at infinity because of the log. So there is no natural boundary condition to put at infinity, and in fact this correlation function is not really well defined because it's blowing up at infinity. Okay? Okay? This here, if you were to compute it using momentum space, for instance, you would have got a divergence, and this lambda would have been part of the cutoff that was required to regulate the divergence. Okay? So everything I've said is correct, but there is this undetermined lambda here, which you very correctly point out. Now, we're going to use, this is actually the reason that x is not a good operator in this theorem, because its 2-point function is not really well defined, blows up at infinity. But we are going to use this as an intermediate step for calculations when we compute correlation functions of things that are well defined, for instance, things that are derivatives of this. And this lambda will always disappear. So it's an excellent question, but it will never play a role in what we're saying. Okay? It will come back actually at some point, but maybe when we compute beta functions and world sheet of the string, it will come back there. But at the moment, okay. Okay, good.
So momentum space, this integral will be something like integral d2k over k square.
Exactly, and that's the reason for the log. Right? You see that it's got divergence with both in the UV and the IR. That's the reason this thing was there. Excellent. More questions, comments? Excellent. So let's keep going.
So when you're doing CFT, why are you interested in putting a cutoff?
We're not interested in putting a cutoff, we're forced to. Okay, good. So you see, let's remember one thing. A CFT is a theory in which the path integral flows to something fixed. But even in a CFT, operators can have anomalous dimensions. Okay? In n equals 4 Yang-Mills theory, for instance, there are the chiral primaries that don't have anomalous dimensions. But there's the Konishi operator, xi, that has anomalous dimensions. Now, if we've got an operator whose engineering dimension is 2, like xi, but it actually has a dimension 2.5, the only way it can have that is by involving powers of the cutoff. Okay? And this happens all the time. So it's not true that the cutoff has no role to play in conformal field theory. That's not true. In defining operators, you often need that. You need cutoffs. It's just the path integral without operator insertions flows to a fixed point, something independent of cutoff. Okay? So that's the kind of thing that we're seeing here, except in this case, it's not that x has a given anomalous dimension, it's just a bad operator. However, the fact that there was this scale dependence there will show up in other ways. For instance, the operator e to the power I k dot x, as we will soon see, will turn out to have a non-trivial anomalous dimension. And that's because of the hidden dependence of this cutoff sitting there. Okay? So we're not first, there's nothing wrong with correlation functions of operators involving cutoff dependence. This happens every time you have an anomalous dimension. Because your anomalous dimension is the statement that the dimensions are not matching on the left-hand side and right-hand side. That's why anomalous. It can only be made up by cutoff. Okay? Good. Excellent. Now that we have this guy in hand, let us use this to compute del x of z, del x of z prime. Okay, yes, let's use this to compute del x of z prime. So let's see, so that is equal to, first we differentiate, let's say, with respect to z. So we get 1 over z minus z prime. Then we differentiate with respect to z prime. Now we get minus because it's z minus z prime, and minus because we're doing a differentiation of 1 over z. The two minuses cancel. Okay? And so we get minus alpha prime by 2, 1 over z minus z prime, the whole thing square. Is that okay? You see, this feature, this object was independent of the cutoff. Went away in the differentiation. Right. We're now going to use this to recheck our commutation relations. Okay, so our commutation relations were alpha m, alpha minus n was this. So let's first write down a formula for alpha m. Alpha m was this, and therefore we'll just use Cauchy's theorem. Z to the power m 1 over 2 pi I integral dx was equal to, okay, let's put square root 2 by alpha prime and maybe a factor of I is equal to alpha m. Is this okay? Okay? Fine. So now what we want to do is to compute the commutation relations of these charges. There was this charge that was integrated over this contour, and then maybe we want an alpha xn, we want commutation relation of alpha m and alpha n. There'll be a similar expression. But you remember that we've learned how to do this. It's the same trick we used when we computed the commutation relations of Virasoro operators. Okay? What was our rule? Our rule was, so suppose I want to compute alpha m commutator alpha m. I take the OPE of the thing that appears inside alpha m and the thing that appears inside alpha n. I take the coefficient of the pole of that OP. Okay? If I always have a 2 pi I, that the 2 pi i's will work out, I take the coefficient of the pole and integrate that over sigma prime. Okay? So what we want to do is to find the pole. Okay. So first thing we have these irritating factors. Let's deal with them first. So that's 2 by alpha prime into minus. They're just out there. Okay? I'll put them back later. Minus 2 by alpha prime. Then I want the coefficient of the pole. 1 over 2 pi I is what we want so that this rule works. So the 1 over 2 pi I is gone away. Okay? So I want the coefficient of the pole was z to the power m del x of z and z to the power n del x z prime to the power n del x of z prime. I want to take the OPE of these two guys. and I want to pull out the pole. But I know that the only singular term, okay, the only singular term in this OP is this guy. Okay? Because, how do I know it's the only singular term? How do I know it's the only singular term? You see, except where z is equal to z prime, okay, except where z is equal to z prime, del squared of x was just 0. That's what the Schwinger-Dyson equation told us. Okay, so we could have singularities. That del square of z is equal to 0. Okay, this quantity admits singularities only at z is equal to z prime, and we pulled out the singularity from that. In fact, okay, I've not maybe completely shown that it's the only singularity. We will see this in a minute because nothing else will have singularities with it. When we work out the normal ordered expansion of these things, we will work. Okay, so sorry, maybe I've not completely shown that it's the only singularity, but believe that for a minute, that there's no other singularity apart from this. Okay, so if we believe that, we've got z to the power m del x z prime to the power n. Then now we have minus alpha prime to the power 2, 2 minus 2 by alpha prime. So those cancel. Okay. 1 over z minus z prime, the whole thing square. Okay. I want coefficient of pole. So I'm supposed to take this guy. I was supposed to take this guy and expand it around z prime till I get coefficient of pole. So to do that requires me to do first order Taylor expansion. So the coefficient of the pole becomes m z prime to the power m plus n plus minus 1. Is this clear? Then this has to be contour integrated with a 1 over 2 pi I. So we get m contour integral z prime to the power m plus n minus 1 by 2 pi I. But this is equal to m into delta of m plus n by Cauchy's theorem. And so we've recovered the commutation relation that we had before. Okay? So this commutation relation that we first got from canonical quantization, you see, we can as easily pull out using Euclidean methods and the Schwinger-Dyson equation, using contour manipulations. As we proceed in our study of conformal field theory, we will often use the second method rather than the first. First, because it's sometimes easier. This is actually to get the numbers straight was very fast here. Second, because we often will not start with a conformal field theory for which we have a classical action. We won't know how to do the canonical quantization. But this kind of method will always work. Okay? Excellent. So,
Expectation value of 2 point from any operator over an OP.
yes?
Can we take it as a OP? It's OP.
Yeah, it's the term in the it's the term proportional to identity in the OP. It doesn't capture everything. If it has another operator there, that will not be captured by this. Okay, but so now let's address this question and the one that was left over from, was this the only singularity? Okay. The next thing we're going to do in the study of these theories is to define composite operators. So you see, even though we're studying a free theory, a theory that you might have been convinced you knew everything about, you see we're going to encounter quite nice things. Things that you'll realize you may not have known. Okay? So the next thing I'm going to do is to try to define the spectrum of operators in this theorem. Okay, so I've got an operator which is, let's say I've got an operator like del x. This is a nice operator, fine. But what about an operator like del x times del x? How do I define that? You might think, well, what's the problem? If it's just del x times del x, put that inside the path integral. The problem is that if del x times del x and del x are both evaluated at the same point, any correlation function involving them is always infinite, as we can see from Wick's theorem, because we'll get expectation values where del x contracts with del x if it's the same point. We'll get 1 over z minus z prime squared evaluated at z equals z prime, which is infinity. So if you take that naive point of view, just setting this operator, to say that an operator is defined by just plugging in the naive expression into the path integral, you get an answer that makes no sense. Okay? So when we define, so what is an operator? Well, it's an insertion in the path integral. When we define insertions in the path integral, we have to define them in such a way that their correlation functions are not infinite. So we need to give meaning to our insertions. Okay. Now there is this very lovely, for free theories, there is a very simple way of giving meaning, which is normal ordering. And in this case, what we're going to define something that we call conformal normal ordering. So suppose I've got some polynomials of del x's or x's. Say del x, del x, del x, del x. Okay? These objects may or may not be at the same points. Okay? Let's say to start with, they're not at the same points. Sigma 1, sigma 2, sigma 3, sigma 4. And later on, we could set sigma 1 equals sigma 2 is equal to sigma 3 is equal to sigma 4 if we want. Okay. Then, so let me start first with two of them. I define the operator which is conformally normal ordered of del x to be del x minus, okay, del x minus 2-point function of del x. So sigma 1, sigma 2, sigma 1, sigma 2. Okay? If I had 4 objects, I would proceed essentially using Wick's theorem. I would define conformally normal ordered product of 4 objects to be the object minus what you get by removing every contraction in every one contraction. Let me write it down once. So del x of sigma 1, del x of sigma 2, del x of sigma 3, del x of sigma 4. I want to define this guy. Okay? So the way I'm going to define it goes as follows. Okay. I'm going to define it as x of sigma 1, del x of sigma 1, del x of sigma 2, del x of sigma 3, del x of sigma 4 equals normal ordered del x of sigma 1, del x of sigma 2, del x of sigma 3, del x of sigma 4 plus, now there are 4 terms. I'm going to write down the first and the remaining 3 will be clear. Plus del x of sigma 1, del x of sigma 2, normal ordered del x of sigma 3, del x of sigma 4. Plus 3 other terms where you choose the pairs. Is it 3 other? 5 other terms. 4C3. Yeah. 5 other terms. You choose all possible pairs. Okay? Okay? Plus del x of sigma 1, del x of sigma 2, expectation value, del x of sigma 3, del x of sigma 4, expectation value, and 5 other terms. or maybe whatever. Maybe that's in this case 2 other terms. Maybe 2 other terms. So it's just in pairs and they're equal. Yes, 2 other terms. Thank you. Okay? And you keep going. Whenever you have an expression, a bare expression, you perform all possible Wick contractions. And the coefficients, what's left over after you've done these Wick contractions, are normal ordered. Okay? Were you to doing, suppose you were doing the following exercise in canonical quantization. You write down a non-normal ordered expression of objects and you want to rewrite it in terms of normal ordered expressions. You get an expansion like of this form. Okay? You can treat this as one bit of motivation for our definition. Now the really important point about the definition is as follows. Okay? With this definition, our operators are normal ordered operators are always well defined. So let's look at an example.
So in path integral, we want to put this normal order
We want to put this normal order.
instead of the normal.
Yes, instead of the non-normal order, because the non-normal order will always give us infinity. We want something that will give us a finite number. Okay? So let's look at an example. Okay? Suppose I want to define the operator, suppose I want to define, let's say, 3-point function. Let's say I want to define del x at the same point with del x, again at the same point. You'll see we'll want to do this in a minute. Okay? Now, had I been using just the bare expressions, the correlation function of this guy, so this is at sigma 1, this is sigma 2. The correlation function of this guy would have been given by Wick contractions. So we would have contracted in pairs, and we would have got a term which was this with this, and this with this, which would have been infinite. Precisely that will cancel against this subtraction. Okay? Because what we actually have is that if we define normal order to this guy, this is del x minus expectation value of del x. Okay? And del x, let's say this is at sigma 1, del x at sigma 2 minus expectation value of del x at sigma 2. Okay? So what would we have got? First we would get everything we got from here, which would include this expectation value minus this expectation value times this expectation value. Okay? So let's work this one thing out. Okay? Let's work this one thing out. First, from this term we would have got del x sigma 1 times del x sigma 2. That's this guy. Then from this guy, we would have got, the only way that's left here is to contract this with itself. So we would get minus, let's call this whole thing A. We would get minus A from here. From this guy, we would get minus A. And then from this guy, we would get plus A. Okay? So the terms involving direct contraction of this with this all just cancel out against each other. But it's not like we're left with 0, because we also have terms involving cross contractions. This with this with this with this. Those are non-zero and give us something interesting. But the terms that would have been infinite, any term involving an operator contracting with another one at the same point, cancels out. Is this clear? This is the reason we make this definition. Please go on.
So you are saying that all possible singularities in the product can arise only because of the contraction?
All possible, yes, because we're dealing with a free theory. So the correlation functions of operators is given by Wick's theorem. We're just doing a Gaussian integral. So it's just, if we wanted to compute this 2-point function, for instance, it's just products of contractions. So there are contractions which are singular and contractions which are not. What we want is that all singular contractions cancel out against each other. Right? Otherwise we get infinity. And this ensures that, leaving us behind with non-singular contractions. Is this clear? Please go on. Then there's a genuine singularity. That is the singularity that appears in the OPE of one operator with another. So we take two operators that are distinct and bring them together. There are real singularities. That's part of the theory. But it shouldn't be that, that correlation functions of operators are singular even when two operators are not on top of each other. Okay, that's what this conformal normal ordering ensures. Now there are many ways of doing this kind of thing. You can use dimensional regularization and so on. In this particular free theory, this is a very convenient way because we can do it very easily. Okay, this is the definition we're going to adopt while studying this free theory and also fermions and so on. Is this clear? Okay, excellent.
So this normal ordering is a form of regularization?
It's, if you want, a form of regularization of the composite operator. Really, it's a definition. Okay, were you to work with some other cutoff, what you would do is to put the two operators together, then subtract something, and say this is my operator. So it's a form of regularizing and renormalizing the operator. Yeah, it's a renormalized composite operator. Okay, and the question you might ask is, why do I have to do it? It's clear, right? We don't want infinity as the answer to correlation functions. That makes no sense. That's a useless answer. We want something that gives us a finite answer. That's all that's going on here. Okay? So this is what composite, this is the issue with composite operators in a quantum field theory. You may think that all you're doing is putting phi squared inside a path integral, but that makes no sense. So you need to give a definition. In this particular case, it's a very simple definition we could give.
You have to usually use smeared operator, right?
You do all kinds of things. I mean, in actual practical calculations, people use dimensional regularization. Okay? Conceptually, what you're always doing is this. You're always drawing a sum of actual insertions whose correlations are finite. Here, I'm doing it in front of your eyes. Okay? I can do it so explicitly here because it's a free theory. And in a free theory, all correlation functions are just given by Wick contractions. This I know. So I subtract away the divergent Wick contractions, I'm done. Okay, this is why it was so easy. Is this clear? Okay. Now that we have, okay, by the way, there is this other lovely thing we can say, which is x of sigma 1, x of sigma 2 as an operator. I'm writing x, but you can think del x if you don't like to deal with the singular operator x or make any difference. This is equal to conformal normal order x of sigma 1, x of sigma 2 plus 2-point function x of sigma 1, x of sigma 2. Right, I've just taken the relation we had before. I'm just writing it again. Okay. Now, you see that because singularities happen only through Wick contractions here, all the singularities that happen here when sigma 1 approaches sigma 2 are contained in this guy. Because the only singularities when sigma 1 approaches sigma 2 is when you contract x of sigma 1 with x of sigma 2. So you see that this operator was, of course, a non-singular operator when you took sigma 1 to sigma 2. Okay? So if we take the OP of x of sigma 1 with x of sigma 2, that OP is very simple. It's this normal ordered operator plus this. This was the 2-point function we calculated up there. That was singular. But this guy is completely non-singular when sigma 1 approaches sigma 2. And this justifies the statement I made above there, that the only singularity in the 2-point function when x of sigma 1 approaches x of sigma 2 is given in the expectation value of the 2-point function. Because the rest of, this is the OPE expansion for x of sigma 1 and x of sigma 2. Okay? What remains is to then take this guy and Taylor expand it. We can Taylor expand it completely naively because it's completely non-singular. Okay? The only singularity is here.
Would it be something like O by Z1 minus Z2 raised to power where the expectation value of O is 0?
I can't hear you.
In the OPE of x1, x sigma 1 and x sigma 2, couldn't there be something like O of Z by Z1 minus Z2 raised to 4 and the expectation value of O is 0?
Is Z?
The expectation value of, like, I'm saying the OPE is something like, the most singular term is O by Z1 minus Z2 raised to 4 and the expectation value of O is 0.
Well, O is an operator, right? It has an expectation value. It doesn't have an operator. Okay, first here we've just computed what it is, right?
Yeah.
It's not a question of could it have been or not. We know what it is.
Yeah.
Okay? So this is what it is. Now, perhaps your question is about a more general theory?
Yeah, in general.
In general. Okay, so suppose you've got an operator whose expectation value is Z.
Is 0.
0.
Yeah, I'm saying the OP is something like O by Z1 minus Z2 plus some identity by Z1 minus Z2.
Yeah, O by Z1 minus Z2 to the power 4. Right. Here I just showed that doesn't happen.
Yeah,
Because it was a free theory. Yeah, in general it could be. Of course, that it's more singular than the identity would have to be the statement that O has negative dimension. So maybe you wanted something less singular than identity. Right? Okay, so maybe you wanted something like 1 or something like that.
That cannot work
Because of symmetry. Okay, yeah, but in some general case you want something. It's the general point that you cannot detect all singularities from 2-point function is true. That is definitely true. In this particular case, we needed an argument that was the case. And this is the argument. In general, it's definitely true that 2-point function is not the only singular. That's absolutely right. Okay, yeah. We'll see many examples of that. Yeah. Okay, other questions or comments? Excellent. So let's say immediately put this to, oh, we're getting late. Huh? Let's, 10 minutes more if you don't mind.
So the question was how to define normal ordering for
No, I think the question, if you please tell me, but I think that the question was, suppose we have we know the 2-point function. Does that capture all the singularities in the operator product expansion of the two operators? And the answer is generally definitely no. In this case, it is yes. The answer is yes. Okay. Okay. Now, I'm sorry I've gone over time today. We'll just go to 3:30 and I'll stop. Okay. I wanted to use our understanding of normal ordering now to compute the correlation functions of a very nice operator. Sorry, the OPE of a very nice operator. Minus 1 by alpha prime del x del x. Now, first, what is this operator? You see, if you compute the stress tensor of our theory, we do it by differentiating with respect to the metric. Okay? Now, we have already seen that the stress tensor, have we seen this? Let me compute the stress tensor. Okay, up to a normalization which we'll fix to be useful. Okay, we have square root g alpha beta, del alpha x, del beta x. That's our action. So the stress tensor of the theory is defined by the derivative of the action with respect to g alpha beta, and then set g to 1. Let's say with respect to upper if we want lower stress. Okay, so one term is just del alpha x, del beta x. The second term comes from here. Okay, this gives us minus half. The half is because there was square root g. Okay, g alpha beta, and then del x, del x. Is this clear, or do you need more justification? You know, I'm using this famous formula for variation of the determinant of determinant of an object, which is g inverse times delta g. Okay, and determinant, if you increase g inverse, you're decreasing determinant of g, because you're increasing g inverse, you're decreasing g. That's the minus. Is this clear? If you let me go on, we'll. Okay, good. Okay, so the stress tensor is this. Now let's take trace of the stress tensor. Trace of the stress tensor is del alpha minus del alpha, which is equal to 0. So classically, at least, okay, our stress tensor is defined by this quantity and is traceless. If we go to holomorphic coordinates, this tells us, you know, z bar was the trace. So it tells us that there's a z component of the stress tensor and z bar component of the stress tensor, but no z bar component. Okay. Now the stress tensor is proportional to 1 by 4 pi alpha prime, but educated people put a 2 pi in front of this definition. I never quite done. Anyway, there's a 2 pi. There's a 2 pi, maybe an I, and so on. So, so when you do that, the 2 pi and 2 pi cancel, so you'll have 1 over 2 alpha prime. Okay, then we're going to, so there's a 1 over alpha prime, maybe with the 2, but then we go to holomorphic coordinates. So perhaps it's plausible that what you'll end up with is this normalization. Anyway, this we'll check independently that it has all the right properties. Okay, so this quantity we're going to call Tzz, or just T. Okay, you follow through the normalizations that come from Noether's theorem, the ones that you want for what we wanted for you know, stress tensor generating translations. You will get this guy. Okay, so now let's quickly compute its operator product expansion. I gave you an abstract argument 2 or 3 classes ago for what this operator product expansion should be in general. Now this is a concrete theory. It's truth time. Either it works or it doesn't. Okay? So let's go. So what we want is operator product of expansion of this. So we get 1 alpha prime, the whole thing square. And then that's just outside. Del x of z, del x of z with del x of 0, del x of 0. Okay, this is what we want. Now, because this was normal ordered, any contraction of an operator that occurred between the 2 normal ordering signs is not there. Those are precisely the things that are subtracted out. But all the cross contractions are not subtracted out. So what we want to do is all possible cross contractions. Okay, how many cross contractions do we have? There are just 2 cross contractions. There's this and there's this. So I could either contract this and this and this and this. Yeah, so there are 2 options. So we're going to get 2 divided by alpha prime, the whole thing square, times, now there's one term which is, you have cross contract only one pair, or there is another term where you cross contract both pairs. Okay? When I cross contract only one pair, I have 2 choices here and 2 choices here, but which to contract? So I have 4. Then I have the 2-point function del x of z, del x of 0. And then what's left behind is the normal ordered operator, del x of z, del x of 0. Plus, I have the term where I contract both away. Okay, so plus I have 2 times del x of z, del x of 0, the whole thing square. Is this clear? Okay, now let's just work these out. So this guy is 1 over alpha prime, the whole thing square. This guy we computed somewhere up there was, where did we have it? Minus alpha prime by 2. And then this guy comes with a 4. So minus 4 alpha prime by 2 times 1 over z square, right? Great. Times normal ordered del x of z, del x of 0. Plus 1 by alpha prime, the whole thing square. Then there was a factor of 2. Then this guy comes with a factor of 2 square, minus alpha prime by 2, the whole thing square. Okay, and then 1 over z to the 4. So let's take that last term first. That is half by z to the 4, because there's 2 and then there's 1 over 2 square. Alpha primes cancel. Okay, plus there is this guy, del x of z, del x of 0 by z squared. But within normal ordering, we can Taylor expand at will because there are no singularities. So let's Taylor expand this out. So you get 1 over del x at 0, normal order. Plus, we have del 2x of 0, del x of 0, normal ordered. Both of these come with a 2 and by z square. Z. Thank you. But this guy is just del of. So this guy came with a 2 also. This had a 2, right? This was del, not 2. Del square. I just take one del out. I can do that by eating up the 2 because if I take it out, it could have acted on either. So this is the same as this, del of this. Okay. And now what about my alpha primes? I had here 1 over minus 1 over alpha prime. And also here plus minus 1 over alpha prime. Right? Because from that, we've accounted for the 2, but we didn't account for the alpha primes. Okay? And so we get half divided z to the 4 plus 2 into minus 1 by alpha prime del x by z square plus 1 times minus 1 by alpha prime del of del x by z. But this is just t, and this is just del t. And so the answer was c by 2 z to the 4 plus 2t by z squared plus del t by z, provided we identify c is equal to 1. So we see that this quantity has the expansion of the stress tensor, has the interpretation of the stress tensor, more or less this up to numbers we saw, anyway, should have been the stress tensor. But it's the stress tensor of our theory, okay, has the right OP for a stress tensor. And in addition, this calculation tells us that the free boson has C equals 1. Okay, I suppose we should stop. I think we should stop, yeah. Okay, okay. Yeah, I had hoped to complete our discussion of the free boson today, but maybe not. Next time. Next time we'll complete our discussion of the free boson, this non-compact free boson. We'll also discuss the compact free boson. And then we'll start discussing free fermions, heading towards Bose-Fermi duality.
What's the dimension of X?
X is not a well-defined operator. So the question doesn't have good meaning. The dimension of del X is 1. So in that sense, you might think dimension of X is 0, because del of X has dimension 1. But X, it's an excellent question. You see, how do we know what are the good operators in the theory and what are not? Well, the state operator map gives us a great way. To every state in the Hilbert space of the cylinder, there is an operator associated. And there is no state associated with the operator X. We will examine this as we go. Okay.
And if we take the expansion of X,
Yes.
do Z going to lambda Z, can we see some factor of lambda coming out of the expansion?
Okay, excellent. Yeah. Yeah. So let's write out your question. Okay, I'll have to clean some. What was our expansion? Our expansion was del X was equal to, what's it, alpha prime by 2 minus alpha. Sorry, there was some, I'm ignoring the factors. Okay, sum over n alpha m by z to the power m plus 1. Okay, now if you want this guy to scale like dimension 1, this guy scales like dimension m plus 1. So this guy had better scale like dimension minus m. So if we associate dimension minus m with this operator, then this whole thing scales like dimension 1. So that's the thing that works. If under a scaling, this also has to scale, and then the whole thing scales like dimension 1.
Then the X won't have any dimension.
Then X won't have any dimension. Yes, X won't have any dimension except that it's not an operator. You know, the way to check whether X has dimension is to compute its 2-point function. The 2-point function of X is not well defined. It's not well defined without, as Omkar pointed out, a cutoff. You know, so it's just not a number. Okay? That's why X is not a good operator. Okay? We will see this in multiple ways. But of course, you can secretly think of it as having dimension 0. Don't tell anyone about what you're thinking, and you'll never go wrong. Okay?